It's really annoying when you're about to work on fixing something electronic and your tools break down on you. This happened to me this week with my 3325a synthesizer function generator from Hewlett Packard. I recently moved, and as part of setting up a new lab, I installed a switched outlet for some of my lab equipment. This is a feature that I wanted because roughly half of my equipment drains a significant amount of energy even when it's powered off. As well, there's a noticeable 60 Hz hum on some of this stuff, which is fine in a lab environment, but it's not so great at home. The 3325 was working fine until I tested out the switch power. It seems like something went pop the first time I cycled the power, and now it no longer works. You can see that when I press the power switch, you can hear the fan comes on, but only a flash on the display appears. So I'm going to pull this thing apart and I'm going to do my best to get it working again. Well, here it is, the inside of the 3325 function generator. I'm going to start at the top. This is where the action seems to be. We have our power supply here. We've got a logic board here. And then on this side, this is actually the main frequency generator board. Let's take a look at the symptoms that we have. So I'm going to plug in the generator, and you may be able to hear that, but there's a nice 60 Hertz hum happening right now. And if I try to power this up, yeah, the fan starts up, but I've got no lights on the front display. Now, the first rule of any repair job is always check your voltages. As Dave from EEV blog likes to say, thou shalt check voltages. So let's do exactly that. This is really some old school engineering, and that's great because all of the test points are marked on the power supply board. So I'm just going to go through each one and we'll see what we get. Now there is a bit of a hum, so I'm just going to try these first without the power on and just see if anything shows up. And no, the meter's still floating there, so nothing too exciting. Okay, so let's power it up, and I'm going to check my plus 15 volts, and we got 15.052, which is really close. Plus 5 volts, 5.0899, again, really close. Minus 15 volts, yeah, that's minus 15 volts, all right. So now we've got 15 plus 15 here. This is unregulated, and we've got about 20 volts on it, which is good. And then we've got a 5 volt unregulated. So these all look good. Now the power supply looks fine, but the problem could be due to ripple. So I might check that later, but there's one more test I'm going to do, and it's this connector here, because this machine actually has two independent power supplies. So there's this main power supply which has 15 and 5 volts out, and then there's a little power supply on the side here, and this is used to power the GPIB interface. And actually this whole area of the board, it's all electrically isolated from the rest of the logic board. So you can see here there's sort of a row of opto-isolators, and that prevents any of the currents going from this side of the board to the other side of the board. So I'm going to check this power supply out and see what we get. Let's first just, we'll go on to a pin of any one of these chips and see if we get a nice 5 volts. And yeah, we're getting something funny for sure. Minus 4. Doesn't even make any sense. So something's odd there. I'm going to try another power line here, just a random one. And what do we got? Minus 4 volts as well. Oh, wait a second. The ground is connected to the wrong place. So I'm just going to tie this ground onto the on the heat sink there, see if I can do that. Perfect, so that's grounded. And let's check one of these chips again. And we get -3 volts to the -3rd power. So that's like 33 millivolts. Not a lot. Okay, I'm just going to try another chip here to see if I get anything else. And we're basically getting the same thing. Okay. So that's interesting. So I'm going to check and see the input to the power supply section and see if it's actually getting input power. So I'm going to switch to AC volts. There we go. And I'm going to just probe directly on that input plug. See what I get. And 9.2 volts. And that is, you know, should be right. Like 9.2 volts. It's going to regulate it through this regulator here, give us about 5 volts out. But for some reason, we're only getting 33 millivolts. I'm going to guess the problem's in the section here, and I'm going to adjust the camera so you can take a look. Here's the power supply for the GPIB interface. The input is here, and that's a 9 volt input. Then there's a little tiny capacitor right there, which is, I believe, across the 2 input pins. Then we have a bridge rectifier right there. A big old capacitor, looks like a 470 mic. We've got a regulator, and then we've got an output capacitor, and then there's a couple other things here. It could be any of these components here. Most likely, it's going to be these capacitors based on the age of the machine. It's 30-something years old. So what I'm going to do is I'm going to pull this board out, and I'm going to test these capacitors, and we'll see if they are good or not. And if they are bad, I'm going to replace them, and hopefully this thing will fire up. Just to go over what's on this board, on this side you've got your GPIB interface, you've got your power supply for GPIB, you've got opto-isolators halfway through the board, and then on this side you've got all of the logic components to control the generator. So this is basically a computer, I don't know, I'm assuming it's an 8-bit computer of some sort, that does all the work of, you know, giving this thing a personality. There's a cable here which goes to the keyboard at the front, and then there's these cables here that go to the other boards, so the frequency generator boards, the relay control boards, etc. They're here. Here we've got a cable that goes to the GPIB connector on the back of the unit. So I'm going to carefully pull this thing apart. I've got a few tools to do that. I've got a IC extractor for these cables. Got my handy dandy screwdriver, and I've got a relatively new Phillips screwdriver to pull this out. So let's get at it. I really don't like pulling these out because the pins can bend. I think this is a stupid way to connect cables. And as much as I love HP equipment and any equipment of this era, this connector type is a bad decision that I'm glad has gone away. I just got to do this really carefully. Oh, it's coming out, coming out. I've bent the pins on these before, and yeah, basically it's a mess. Okay, so we're out. Okay. One of the great things about this board is that it's actually a very high-end piece of equipment, and as such, all of the traces are gold-plated, and it's not masked at all. You could probably melt this thing down and, you know, get 20 bucks for the gold. I'm not ready to melt anything down yet, so I won't be doing that, but you know, if this repair doesn't work out, you never know. Okay, AC input is off. I'm really scared of this connector here and these ones. Come on, come out. Oh, this one's easy. Yeah, this one's not bad. Okay, we got it. And out of the way. And then these ones, I'm going to try to just jam this here. Underneath. Nope. Let's see if I can just use my hands and kind of work them. Oh yeah, sort of coming. Putting a lot of force on this. Can you hear that? There we go. It's out. Now, did I bend any pins? No, it looks like they're okay. So that method seems to work. So I'm gonna rock this one back up. That one came out easy. And I'm gonna rock and roll this one. Oh, that one came out a little too easy, in fact, and it did just ever so slightly bend that last pin, but it'll be fine. Okay, now the last bit is this power connector here. Let's just put our screwdriver in there. There we go. Now we're disconnected. There is one little ground tie-in cable. It appears to be a ground just going to the case. Yeah, it must be. That I'm going to leave connected for now. I don't really want to remove it. Okay. And place our screws aside here. I think there's 5 of them. Let's try to do this. There we go. And number 3. Oh, there's 6, it seems. There's actually one hiding here. Oh, there's 7. I keep finding them. Hey, it's HP from the 70s. Before the $300 per gram ink company they turned into. They were actually a good hardware company. And look at that. I mean, I'm counting, I've got 5 screws so far. And these are all just to hold this logic board down, which is awesome. This is not how I engineer things. Typically, I'll put in 1 screw and hope for the best. This, guess I would never be able to work at HP in the 70s. I think I could do it now though, because, you know, again, crappy printer company charging you for your ink. Okay. What the heck? I'm at 9 screws so far, and I see 2 more. There's number 10. This is insane. Insane in a good way. Number 10, and there's number 11. Oh, the board started moving. This is a good sign. What do we got here? Is it going to come out? Oh yeah, she's coming out. Look at that. You know what this reminds me of? This actually reminds me of like a IBM PC motherboard, you know, from this era. Here's a closer look at the board. It's basically, you know, a little computer. So here's a CPU of some sort. It looks to be a custom chip. It's on a nice ceramic casing. Looks like it's been built either by HP or for HP. Probably by HP at this time. There's what appear to be 4 ROM chips. And then we've got a whole bunch of 7.4 series logic all over the place. I've got the board flipped over and I'm going to be testing these 3 capacitors in the power supply. There's this 470 microfarad one, 1000 microfarad one, and there's a little tiny ceramic or tantalum or something like that, one at the end. So let's test this tiny one first. See what we get. And we're getting 93 nanofarads, which is probably okay. Okay, and then I'm going to test the 470 microfarad. And we're getting 410 microfarads, which is within range for sure. And we'll test this 1000 microfarad one. And we're getting 667 microfarads. So that's actually quite low. That might be an issue. The next test I'll do is I'll do an ESR check on these. Can't really do one on this tiny capacitor. It's not going to make any sense, the measurement. But I'll test this one out, and we get 602 milliohms. I printed out a handy dandy chart, sort of a cheat sheet, and looking at it's 1000 microfarads is supposed to be 16 volts, so it should be 0.15 ohms, which is 150 milliohms. So this 600 number is 4 times higher than what we are expecting. That's not good. So it's got 2 strikes against it right there. And then this guy here, we're getting 600 milliohms, and this one is 470 microfarads. It's 6.3 volts. It should be something like 0.3, so it's at least double what it should be. Given that, I'm going to pull these 2 electrolytics out. When you're measuring in circuit, even with an ESR meter, sometimes your results will vary. So you're not necessarily going to get a perfect measurement when it's in circuit. It's a good guideline, but it's not always 100%. In fact, often it's like nowhere near 100%. So I'll pull these out, measure them again, and we'll see what we get, and then we'll replace them if they're indeed dead. Come on. I have a proper desoldering tool, but it is broken. If you don't have a desoldering gun, generally speaking, desoldering braid's the best way to go. Those little suction tubes and whatnot, like little bulbs, or they had a little vacuum one that's spring-loaded. I think they're totally useless. So I've connected this capacitor to my ESR meter, and out of circuit we're getting 560 milliohms on ESR, so about 4 times higher than it should be. And our capacitance is 719 microfarads, which is 30% lower than it should be. So it's out of spec for sure. Probably bad. Replacing it ain't gonna hurt. So we're testing the other capacitor. It's supposed to be 470 microfarads. And we get 407 microfarads, that's fine. The ESR is 662 milliohms, which is about 4 times higher than what it should be. The important note here is that the measurements out of circuit were different than what they were in circuit. So even with a proper ESR meter, your in-circuit readings are going to be different than your out-of-circuit readings. And to some degree, you know, there's luck involved whether or not you'll be able to measure your components within the circuit. So I do have some replacement parts here. I've got a 1000 microfarad, and I've got a 470 microfarad capacitor I got from DigiKey, and I will solder these in. We can see what happens. And again, we got to be very careful that we get negative to negative, positive to positive. Bend those over a little bit. And let's fill that guy full of solder. Bit dirty. Done. And done. Get this board repositioned. Got new capacitors in there. And we will screw it down. I probably should take a look at those other capacitors, but you know what? I'm not gonna right now. I'm just gonna see if this fixes the problem, and then I will decide if I should recap the whole unit. Okay, we're reassembled. Let's plug this in, see if it smokes. Whoa, 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 whoa. Take that. Make sure that stays out of the way there. Okay, plug it in, let's see if smoke comes out. Double check. We're all good. We're good. Okay, it's humming. And we got nothing. Let's take a look at the display. Almost the same thing. In fact, if anything, it seems worse. Well, that's not good. That's frustrating. I'm going to pull the first capacitor, the tiny 0.1 microfarad cap out. It's just a filter cap, so I think I'm going to just remove it and see if this thing will power up with that removed. I don't actually need to get both pins out, but I want to. There we go. She's out. Where is she? Not quite. Come on. There we go. Got it. So there is the little guy. And I'm just going to make sure that that connection's clean enough. Looks good. I just want to make sure it's not shorted. And I'm going to clean that up, and I'm going to leave it removed because it is a filter cap. And, you know, I would expect this to come up with that removed, but it might not be 100% perfect performance when we do so. So let's see what happens. Okay, so we plug it in. It's humming, powered up, and nothing. We got no display. So again, nothing. Oh, it clicked. Okay, it's not the capacitor. It's not that first capacitor. It's not the other two capacitors. So it has to be either the regulator here or this bridge rectifier. So I'm going to check my voltages on the regulator inputs. One thing I found out is there's actually a constant 9 volt AC on this plug here. And that probably makes sense because I think with this unit you can wake it up with GPIB. So it would need to have this portion of the circuit board active at all times to listen for those wake-up calls. I think that's correct. I might be wrong. Comment down below if I am wrong. Wouldn't be the first time. Let's do this here. This hook kind of works. There we go. It's hooked up now. So that is my positive lead connected up to the probe. There, I'm going to put that off to the side. And then negative, the ground is easier because I can just clip onto this heat sink here and clip my lead onto it. Perfect. So I'll put that off to the side of the scene. Okay, we'll plug in the machine and we see on the voltmeter it's ramping up 0.9 volts, 1 volt, 1.1 volts, 1.2 volts, Going up 1.3 volts. It's slowly going up. This is my input voltage, 1.34, 1.35, 1.36. It's just ramping up. 1.4 volts. Hey, maybe if I let this sit long enough, it'll actually work. We're going to need about 6 volts on that input. What do you think? Think it'll get there? It's not supposed to do this, I'll say that much. 1.43 volts. That is the weirdest thing. So what's going on here? We have power coming in, AC coming in there. I'm just working through this in my head. I just don't know what the heck is going on. AC and 9 volts going in there. We have a bridge rectifier there. It's charging, slowly ramping up the voltage. So how is that happening? I just don't know. I mean, you know, it could be there's something wrong with that bridge rectifier. Is it getting hot? No, not getting hot. It's not the capacitors. It could be something downstream, potentially, like a short or something that's, you know, causing an issue. So, you know, I could take the load off of the power supply somehow. But maybe what I'll try to do is I'll try to bypass, I'm going to bypass this bridge rectifier because I don't think I have a spare. I might have an old power supply I can pull one from, but I'm not sure about that. But what I'm going to do is I'm going to solder a couple of wires to where this is. I'm going to remove it, solder in a couple of wires, and I'll apply 5 volts from one of my power supplies directly into there, and we'll see if this thing fires up. I pulled the bridge rectifier off the board, and before I inject power onto that circuit board, I thought I would test it out of circuit just to see if it was the problem or not. And I've wired it up to a 10 volt AC power supply. I've got my oscilloscope wired to it, and we can see on the trace coming out of it, it's actually, you know, pretty clean. It looks like there's about, let's call it 13, 14 volts peak coming out of that. It's all DC, so that regulator looks good. Now there's no load on it, so I'm just going to apply about a 200 milliamp load with this resistor here, and no real change. So I walked away and slept on this, and I thought about this last night a little bit. My original plan was to inject power here where the bridge rectifier was, but I proved that the bridge rectifier is good. And what that means is if I inject power here to where a good component was, it's not going to tell me anything extra. We're still going to get the same result. So I have to look for what the possible failed component is. Now the capacitors obviously are good. So it's something else other than that, and it's going to be downstream here. At this point, the biggest candidate for failed component is this regulator here. So I'm going to pull it out, and I'm going to apply voltage to where its pins were, and we'll see if this thing works. Now there's a possibility I could get away with not pulling this thing out and just putting power to those pins, but I'm worried I might blow the regulator up, and I don't want to, you know, kind of destroy something that I thought was the problem and end up, you know, destroying it myself, and in reality the problem is something else. So I'm going to pull it out just for safety's sake. If the regulator is not the problem, the next component in the line is this capacitor, and it's been replaced, so it's not the issue. It could be any one of these chips that failed shorted, or more likely it's one of these small capacitors that have failed shorted. So I'm going to go through, I'm going to replace this, well, I'm going to pull it out, test it out of circuit. I'm going to replace it, inject voltage, we'll see if this machine comes up. The regulator is just screwed onto this heatsink. So I'm going to remove that physical connection. I just lost a washer. I heard it fall. Please, 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 please. No. Well, that's the problem. We're going to have to find that thing. Okay. And I'll desolder this from the board. And I'll find that washer. I've wired my lab power bus that you can see in the background there directly into the board where the regulator was. I've got my ground on the shield here, which is directly into the ground on the board. And then I've got a positive line going to where the positive output of the regulator was. Now that I've got guaranteed good power here, hopefully when I power the machine up, it'll actually start. I'm going to set the power supply to 5 volts. So voltage 5, and we have 5 volts, and it's current limited right now. So let's set the current to 0.25. Okay, and then I'm going to plug it in. And we're draining 212 milliamps on that circuit with the power off. Earlier in the video I said that that side of the board is powered up all the time, and so it makes sense that this would drain 200 milliamps. Okay, we're ready to go. Let's power it up. Fans on, but nothing on the screen. Okay, let's try again. Nope, nothing. Third time lucky. Oh, it flashed, but yeah, it is not working. So I've applied a nice clean 5 volts into the GPIB interface section. I mean, it should be working. Well, I'm not entirely sure what to do next. I guess I will go back to step 1 and start checking voltages again, see what I get. Okay, so we'll test right at the regulator output, and we're getting a nice 4.938 volts. And I'll test this chip here. Be careful. 4.9342. Gonna test here. 4.332. 4.9332. Test here. What we got? 4.9328. Test here. 4.9330. All these voltages seem to be within spec, so I'm not entirely sure what to do next. But I'm not going to give up quite yet. I'll keep looking, and hopefully I'll make some sort of breakthrough. Okay, so this is interesting. I actually got this thing to start up once, and I think I know what the issue is. I think the problem is I need to screw in the rest of the screws that hold this thing down, because if you look at the traces on the board, these screw holes are like suspiciously fancy, and they're all tied into the ground planes. Not all of them, but like most of them are. And I'm guessing that the screws and their connection to the chassis forms an integral part of the circuit. So working with that theory, I'm going to pop all these 11 screws, which I've been avoiding, by the way. I'm going to pop those into the board. First thing I'll do is I'll unplug the power. Don't want anything to blow up here. Don't want anything more to blow up here. And I'm going to put all these screws in. And you know what? In fact, there's so many, I'm just going to use my handy dandy drill, set to the lowest torque level, and we'll pop them in quickly. Okay, it's all connected, ready to be powered up. Let's see if it turns on. And would you look at that? We've got a 1000 hertz signal. That is just awesome. And so the problem was the screws were not all installed after I did the testing, after I replaced the capacitors. So all this stuff I did with the regulator and with the rectifier, totally unnecessary. All I really needed to do was to screw in all the screws, and it would have been a much quicker repair. After the repair, I noticed it was a little bit flaky, so I ended up replacing the voltage regulator as well, and now it seems to be pretty much rock solid. So I'll run through some basic tests here. 1000 hertz, we'll set our amplitude to 100 millivolts, and we'll get the scope fired up there, and you see we've got a nice sine wave, and the scope's saying it's roughly 1000 hertz. The frequency counter on the scope's not super accurate, so that's fine. I'm going to change the frequency to 1 megahertz. Yeah, let's do 10 megahertz, why not? And set the scope again, and a nice clean sine wave at 10 megahertz. I'll go back to 1000 hertz and auto set once more, and then we'll switch to square wave. Nice square wave coming out. Triangle waves, they all work as well. So it looks like a successful repair. Well, there you have it. The 3325 has officially been fixed and will be put back in service. The problem was the bad capacitors on the GPIB power supply. The secondary problem was that when I tested the unit after replacing the caps, I didn't install all the screws that hold down the main board, and these screws form an integral part of the circuit. There's a few more caps on the main board I wouldn't mind replacing, but I'll leave that until I get my desoldering tool repaired in a week or so. I hope you enjoyed this video, and if you like what my channel has to offer, please consider subscribing. I'd really like to make more videos and further finance my descent into retro equipment madness. So to do that, I've taken the plunge and I've actually gone and opened a Patreon account up at patreon.com/retrologiclab. I don't have any patrons yet, but who knows, maybe you'll be the first. Thanks for watching, and ciao until next time.